So good evening all. So welcome to the 8th week's problem solving session on modeling and simulation of dynamic systems. My name is Parth Joshi. I am a PhD student in the Department of Mechanical Engineering at IIT Bombay. Uh, so I am also a recipient of the Prime Minister's Research Fellowship, and as a part of this fellowship I got this opportunity to interact with all of you and conduct these online weekly problem solving sessions. So in today's session, we will be discussing problems related to uh, the topics that have been covered for the 8th week's content, which is uh, so firstly, we will be discussing problems related to uh, system identification, like least square parameter estimation, and then the other content which is related to optimization. So in this content for week 8, so we first we have the content related to estimation methods like least square parameter estimation methods, which are used to estimate some of the model parameters from experimental data. Then the methods of system identification have been discussed. So where we use experimental data of for to get the model. So if we have like experimental data of the input and output quantities for a given system, then we can use that experimental data and start like we can assume a certain model structure and then find the parameters of the model using system identification methods. So that has been discussed in this week. And also the methods of optimization have been introduced. So some of the concepts related to optimization, basically the basics of the things which are involved in optimization, which are basically the definition of the design variables, then the identifying the constraints, then defining the objective function. So within constraints also there will be inequality constraints, equality constraints, and also bound constraints, or which are also called as side constraints. So with all these things together, we can basically narrow down and like come up with a feasible design space, and then use different algorithms or search techniques. So some of them are called as direct search techniques, some of them are called indirect ones. So some of those have been discussed. Now, particularly with respect to the objective function, we can classify them as uh, linear programming or non-linear programming, depending on the nature of the uh, objective function of the optimization. Then, depending on the nature of the constraints, whether there if there are no constraints, uh, then we can call it as an unconstrained optimization problem, and if there are some constraints, we call it as constrained optimization. And then also will like the non-linearity may not always be necessarily with respect to the objective function only. Some of the constraints can also be non-linear. So so that is also one of the uh, one of the considerations. Yeah, hi. So I think we have one more person who has joined. So hello, hi, good evening. Uh, Welcome to the session. So yeah, so I was just basically trying to summarize what is the the what are the course contents for this week, and then so I just gave a brief background about myself. So basically my name is Parth Joshi, and I have been basically conducting these weekly problem solving sessions, and today we'll be discussing problems related to the week 8 content. Yeah, so any questions or comments before we begin? So any questions or comments that you would like to raise? Okay, I think then we can get started. So my plan for this session is basically to uh, discuss some of the problems which may be similar to your assignment problems, and so you might come across similar problems, and so we'll try to cover as much problems that, so I have like collected lots of problems, so we'll try to cover as much as possible. And if you have any questions or doubts, like you can raise them. You can raise them in the middle of the session as well. Sure. So let us start with our first problem. So there are certain statements given in this question. So the first statement is that parameter estimation is only needed for models with unknown parameters. The goal of parameter estimation is to find the best fitting parameters for a given model and data. Goodness of fit measures like R squared can help assess the quality of parameter estimates. And then parameter estimation always guarantees accurate model predictions. So which one do you think is a false statement? Yes, so yes, you are correct. So parameter estimation does not always guarantee accurate model predictions. So sometimes we may, depending on what our model structure that we have assumed, it may not, and also depending on what are the data that are available to us for estimating the parameters. So it may not always be fully accurate. It actually depends on the model structure as well as the data which we use for parameter estimation. The first statement which is said, like that the parameter estimation is needed only for models with unknown parameters. So yeah, if the parameters are known already, then we don't need to do it. Then yes, at the goal of parameter estimation is to find the best fitting parameters for a given model data. So that is true. And then there are some measures like R square, etc. Those are like methods which we can use, like those are some metrics which we can use to predict how good the a fit between the model and the data is. So that's about this question. So shall we proceed to the next question? Okay. Now the next question is with respect to the regression variables. So we have the equation y is equal to phi of theta. So that is the regression equation between the input and the output variables. So or basically y is the measured quantity, and so we have a regression uh, between the state variables theta. So so if we have q regression variables and p observations, so what will be the size of the matrix phi? Okay, p cross q. Okay, Fine. So we'll see how whether that is the answer. So let us try to write the expression y equal to phi theta. So it will be basically we start with, let us say, the first observation y1. So which is y11 theta 1 plus y12 theta 2 and so on. And since we have q regression variables, so our last one would be similarly we can write y2 is equal to y21 theta 1 plus y22 theta 2 plus. So likewise we have p observations. So we will be basically having p rows and there will be q terms in every row, so which we can represent as a multiplication of matrix of with q column vectors. So likewise we will have y so so from this we can write it as, so basically, so the matrix y will be p cross 1, which is phi, and the matrix theta is q cross 1. So therefore matrix phi should have p rows and q columns. So therefore the correct answer to this question is C, p cross q. So now let us proceed with our next question. Now in this question we have been given two statements p and q. So we have to find out which of these statements are correct. So least square method can be used for parameter estimation, and the second statement is the least square method can estimate parameters of both static and dynamic models of a given structure. So which one do you think is the correct answer? Yes, so you are correct. So both statements P and Q are correct. So the least square method can be used for parameter estimation. That is definitely true. And the second statement is also true, that it can be used for both static and dynamic models. Now the next question is least square estimation minimizes what? The summation of errors, or summation of square of errors, or summation of absolute values of errors, or all? Yes, so you're right. So the least square estimation method minimizes basically the summation of the squares of error. So so in the let us now you know look into the slides for related to this thing. So in the slides, so we define first the error matrix E, and then we basically try to minimize the quadratic function, which is sum of the squares of errors e1 square plus e2 square and so on. So which is E transpose E. So therefore the correct answer to this question is that the least square method minimizes the sum of squares of the errors. So the correct answer to this question is B. Yeah, in the next question we have been given again two statements. Time series data is often used for system identification in dynamic systems, and only black box models can be identified through system identification methods. So which one do you think is the correct answer? Okay. Yeah, so let us examine. So you think A is the correct answer? Okay, fine. So we'll check that. So the first option says that time series data is often used for system identification in dynamic systems. So that is correct. So we generally consider the lot of data for the input and output variable over a certain period of time. And so yes, we need time series data definitely. Then the second statement is only black box models can be identified through system identification methods. So this statement is not correct, because uh, the system identification methods can be used for either kind of models. So it may be black box model or white box or gray box model. The thing is that in case of white box models, we know what would be, or we have the in like from an engineering sense, or from engineering intuition and physical laws, like we can guess what is the structure, what would be the structure of the model, and then we assume the parameters and use the data to like input output data and system identification methods to fit a model on top of that. In case of black box model, so we select certain suitable model structure and then tune the parameters using the system identification methods. So there we do not have access, like we are not able to, we do not have a physical understanding of the system, and we do not have, basically cannot derive a model based on physical laws to get the, to guess the model structure. So we assume a suitable model structure and then use the system identification method. And in case of gray box, it will be a combination of white box and black box model. So where we can guess the model structure of and to some extent using the physical laws, and some of the parameters we actually just tune it using the data. So it's somewhere in between white box and black box. So but yes, all the system identification methods can be used for either kind of models. So statement 2 is actually false and statement 1 is true. So the correct answer to the question is A. Yeah, so in the next question is, which identification method involves choosing a standard model and tuning the parameters to the data? So we just discussed that. So which one do you think is the correct type of model in this case? Yeah, so it is correct. So we just discussed this, that black box model involves basically choosing a standard model and then tuning the parameters to the data. The correct answer is black box. So in the next question, we have been given a toy factory in India produces two types of toys, A and B. So they need to produce at least uh, 200 units of A and 150 units of B daily to meet market demand. The profit per unit of A is 300 rupees for A, and for B it is 200 rupees. However, they have only 400 hours of production time available per day. So which one of these side constraints represents the total production time for toys A and B? So we have been given some inequality constraints, and we have to choose which one of those are side constraints which represent the total production time for toys A and B. So we have been given that we need to produce at least 200 units of A and 150 units of B daily. We have been given the profit per unit of A. So if A and B are, let us say, the number of units of A and B, capital A and capital B, let us say they are the number of units. So then which one do you think is the correct answer? D. Okay. So yeah. So first question. So like the first, let us examine that. So the first option and second option are basically inequality constraints, but we have not been given like, let us say, the the number of so we have the constraint on the 400 hours of production per day, and if a, let us say, A is the number of units of A and 150 units of B, to have a constraint on basically the that quantifies the number of hours of production time. So we need to know what is the time in hours required to produce A and B, and so based on that we can like estimate the total production time, but that is not given. So the options A and B are actually not relevant. Then let us come to option C. So where there is an equality constraint. So where A plus B is equal to 400. So this constraint is actually meaningless because if A and B is the number of units of A and B, and 400 is the basically the hours of production time. So this constraint actually does not make any physical sense, because uh, if this is the A and B are the number of units of A and B, then this does not make sense. Now let us come to D. So in D we have two bound constraints or side constraints actually. So where A is greater than or equal to 200, which represents exactly the first statement that we need to produce at least 200 units of A and 150 units of B. So the option D actually represents the those side constraints. So you're right. So the correct answer to this question is D. Yeah. In the next question, we have been given an optimization problem where the objective function is f of x comma t is equal to 3x square plus 5 e to the power minus zero point 1 t, where x is the decision variable and t represents time. So what type of optimization problem is this? Yeah, so you're correct. So it's a dynamic optimization problem. Why? Because time is explicitly coming into the objective function. So the second term in the objective function, which is 5 e to the power minus 0.20, explicitly involves time. So the objective function varies with time. So it's uh, that is why it is called as a dynamic optimization. So it actually depends on time. So the correct answer to this question is option C. So in the next question, okay. So in the golden section, so okay, we'll go through the question. So in the golden section method, how is the search interval updated in each iteration? So first one is whether reflecting the interval, contracting the interval, or expanding the interval, or randomly choosing a new interval. So yeah, so to answer this question, let us just quickly go through the slides related to this. Uh, so let us look at the part where we have basically defined the golden section method. So in this method, we basically try to, so we first choose a certain interval and then divide that interval into two unequal parts. And so in the next iteration, we try to select a smaller interval such that the ratio of the smaller to larger interval is equal to ratio of the larger one to the whole one. So therefore the proportion, like the proportion between the two intervals is as per the golden ratio, so 0.618. So so basically in each iteration we try to reduce the interval of uncertainty by 0.618, and by repeatedly applying this, so we basically try to reduce the value of the uncertainty in the interval. So by that factor, so we reduce it by a factor of 0.618, so in every iteration. So basically we are trying to contract our interval in which we are searching for the optimum. So yes, so the correct answer to this question is that yes, we are trying to contract the uh, the interval in which we are searching the for the optimum. So yes, so the correct answer is B. We are trying to contract the interval. So yeah, in the next question we have been uh, given the linear programming problem. So we have been given the objective function minimize z is equal to 20 x1 plus 10 x2, and subjected to the constraints of x1 plus 2x2 less than or equal to 40. Then the next constraint is 3x1 plus x2 is greater than or equal to 30, and 4x1 plus 3x2 is greater than or equal to 60, and we have bound constraints on x1 and x2 is greater than or equal to 0. So we have been given this linear programming problem. So linear programming as in the objective function is linear in x1 and x2, the design variables, and the constraints are also linear in x1 and x2. So and here since we have only two variables, so what kind of method do you think we can apply to solve this problem? Which kind of method of optimization we can apply to solve this problem? So yes, yeah, we can apply graphical method because it involves only two design variables, so it is possible to solve this problem using graphical method. So we will try that. So yeah, so first, to start with solving this problem, what we need to do is to define, so to draw the the lines which are representing each of these constraints. So we have the bound constraints that x1 and x2 are both greater than or equal to 0. So then we are basically restricting ourselves to the first quadrant of the xy axis. So our feasible region is now reduced only to the first quadrant of the x and y, or x1 and x2 axis. So let us label this axis as x1 and this one as x2. So x1 plus x2 is less than or equal to 40 is the first constraint. So for that we need uh, plot the to plot this constraint. So we need to what we need to do is to basically find out the so how do we find out so how do we plot the constraints so in the graph. So how do we plot the so what is a good method to plot the uh, constraint lines of the constraint in the graph? Yes, so you're right. So we can basically plot the x and y intercept for each constraint line and draw the line which is joining those points like the coordinates of the x and y intercept. So to find that intercept, so first find out the to find out what is the intercept on the y-axis, so or x2 axis. So we'll substitute, let us say x2 is equal to 0. So for that, so for x2 equal to 0, we will get, so on x1 axis we will get 40, and for x1 equal to 0 we will get 2x2 is equal to 40, so x2 will be 20. So the line corresponding to this could be something like this. So now to find out which side of this line, whether above the line or below the line is feasible, how do we find out that? So how do we find out which is the on which side of the line is our feasible region? So first we already know that we have the bound constraints that both x1 and x2 are all greater than 0. So then this is already our so in our we are already in the first quadrant, which is the feasible region. So now to find out which on which side of the line, so whether above the line or below this line is the feasible one. So how do we do that? How do we find out that? So what is a simple way to do that? So the simple way to do that is basically to substitute the coordinates of the origin 0 0 in the constraint and check whether it satisfies the constraints. So if the origin coordinates of the origin satisfy the constraint, then it is on the line like which is so the zone which is below that line will be the feasible one, feasible region. So here in the first constraint, if we substitute the coordinates of the origin, so then 0, it will get left hand side will become 0, x1 plus 2x2. If x1 and x2 both are 0, so the LHS would be 0. So therefore 0 is less than or equal to 40 is correct, which is so it is satisfying the constraint. So therefore origin lies in the feasible region. So therefore the feasible region is below this constraint. Right? So now let us come to the second constraint. 3x1 plus x2 is greater than or equal to 30. So here let us substitute the coordinates So let us substitute x1 equal to 0. So then x2 will be 30. And for x2 equal to 0, so x1 will be 10. So let us use a different color now for this constraint. So this will be the line corresponding to the second constraint. Now again we to find out which one is the feasible region. So let us substitute. Uh, so in the second constraint, let us substitute the origin. So for that 3x1 plus x2. So if we substitute 0 0, so 0 is greater than or equal to 30, does not satisfy the constraint. So the region which is above this constraint is the feasible one for this constraint. So this is the feasible region for this constraint above the line. And now let us come to the third constraint. 4x1 plus 3x2 is greater than or equal to 60. So for this, so let us substitute x1 equal to 0. So then x2 will be, so 3x2 will be 60. So x2 will become 60 by 3, which is 20. And 4x1 is greater than or equal to 60. So x1 so will be 60 by 4, so which is 15. So we will have 15 and 20. So the line passing through 15 and 20. So this will be our line. And so if we substitute the coordinates of the origin, so 4x1 plus 3x2, so 0 0. If we substitute 0 0, then what will be the uh, so 0 is greater than or equal to 60 does not satisfy the constraint. So then the origin is not the feasible region. So the zone which lies above the this line is the feasible one. So now our feasible region is uh, so now to highlight what is our feasible region, so let us use a different color. So our feasible region, so I am trying to draw it using a slightly thicker line, so it will be this. So this will be our, so this is our feasible region. So now generally, so in a linear programming problem, so because uh, so I think I made a mistake in drawing the feasible region. So yeah, let me just correct that. So so our feasible region here will actually be this. So this will be our feasible region. So for that, we need to find out. So generally, the optimum solution will lie at the corner points. That's what we generally say. So let us try to find out what is the objective function value here for each corner point. So to find out, so the let us label these corner points. So let us label this one as A, B, C, and D. Let us say. So generally, we would expect the optimum solution to lie on either of these vertices. So what we need to do is to find the optimum solution, we need to find out the coordinates of these each of these vertices A, B, C, D. So for that, we need to find the intersection point of these lines. So how do we? So we can like in this case, like we can simply uh, solve these linear equations simultaneously. So if we, let us say, number them as 1, 2, and 3. So if we solve 1 and 2 simultaneously, what will be the intersection points? So if we multiply equation 1 by 3, so we it will become 3x1 plus 6x2 is less than or equal to, or let us leave the inequality sign for now. So just for the line, so we will assume the equation of this line becomes, so 40 into 3 now, so 120, and the next equation is 3x1 plus x2 is equal to 30. So if we subtract, so if we subtract equation 2 from 1, so we will be left with 5 x2 is equal to 90. So x2 will be what? So what will be x2 in this case? 18, right? Sorry. So x2 is 18, and now if we substitute it in this equation, so let us say if we substitute it in the first equation, so x1 will become 40 minus 2x2. So 40 minus 2x2 will be 40 minus 2 into 18. So 18 into 2 is 36. So x1 will become 4. So the intersection between the first line and the second line is, or basically the black line and the orange line is 4 comma 18. Then the coordinates, so for B the coordinates are straightforward, it is 40 comma 0, and for C as well it is straightforward, 15 comma 0. Now we are just left with the intersection point for between 2 and 3. So for how do we do that? So for that, so let us again multiply equation 2 by 3. So it will become 9x1 plus 3x2 is equal to 90, and 4x1 plus 3x2 is equal to 60. And if we subtract this second equation from the first one, so we will get 5x1 is equal to 30. So x1 is equal to 6. And x2 will be, so what will be x2? So x2 will be 30 minus 3x1. So 30 minus 3 into x1 will be 6 3s are 18, so which will be 12. So the coordinates of so the intersection point will be 6 comma 12. So the coordinates for point D are 6 comma 12. So our objective function value for each, so what we have to do is, like, let us now make a small table now. So let us, so vertex, value of x1, x2, and the next column will be z, which is 20x1 plus 10x2, 20x1 plus 10x2. which is Z. So for A, so the vertex is 4 comma 18. B is 40 comma 0. C is 15 comma 0. And D is 6 comma 12. So what will be now the value of Z for the vertex A? So what will be value for vertex A? So it will be 20, 20 into 4 plus 10 into 18. So 180 plus 80. So, so yeah. So 20 into 4 plus 18 into 10. So sorry, yeah, 260. Sorry. Then the for the next constraint, yeah, so it will be 800. So for the next vertex, so it will be, so what will be it for vertex C? 300, right? So right, so it will be 15 into 20 plus 10 into 0. So yes, sir, you're right. So it will be 300. And for what about for vertex D? What will be objective function value? Okay, so it will be basically 20 into 6, which is 120, plus 12 into 10, which is again 120. So it will be 120 plus 120, or which is 240. So you are correct. So yeah. So yeah, so we now have tabulated the value of the objective function for all these four vertices, and our objective of the problem is to minimize z equal to 20x1 plus 10x2, and out of these four vertices the minimum objective function value is for vertex D, which is 240. So basically the optimum solution lies for vertex D. So basically our optimum solution will be this. So where our objective function value is the least. So the optimum value of Z here will be 240. So the optimum solution is, optimum solution is basically x1 is equal to 6, x2 is equal to 12, or basically at point D, and Z here is equal to 240. So this is our optimum solution. So is that okay? Okay. So let us now proceed to our next problem. So in our next problem, we have to estimate the parameters a and b using the least square method for the model which is given here, y equal to a plus bx. So we have been given the model y equal to a plus bx, and we have basically three different values of, like, three different measurements of y which are available for different like three different measurements for y. So 3 equal to a plus 3b, 8 equal to a plus 4b, and 7 equal to a plus 5b. So we need to estimate the parameters a and b using the least square method for these three measurements. So for that, let us go to the corresponding the section in the slides for this particular problem. So I'm sharing my screen now. So are you able to see my screen? Okay. So are you able to see my screen? Okay. Yeah. So this is the the relevant section in the slide. So here we first, like in the least square problem, we first define the error matrix, which is y minus phi theta. So phi basically is the matrix of the regression coefficients for each measurement of y, and theta is the basically the set of parameters. So y is here like y1, y2, y3, which is our. So let us write down for our particular problem what are the matrices y, phi, and theta. So let us go back to our problem again. Right. So for our particular case, the matrix Y is 3 comma 8 comma 7, which is equal to, so our phi matrix is, sorry, so our phi matrix is this one, and this is our theta matrix, which is equal to phi equal to theta, phi into theta, sorry. Now let us again go back to our slides. So we have defined our phi y matrix, y phi and theta matrices. So let us go back to our slides again. So now in the least square method, we have been given that so we have to minimize the quadratic function which represents the sum of squares of the errors, and so to minimize the quadratic function, so we basically set the derivative of this quadratic function to 0. So dv, so the derivative of this function v with respect to theta, the design vector of the parameters. So then we get this equation phi transpose phi into theta is phi transpose y. So by solving this equation, so we basically get that the least square estimate of this parameter vector theta is phi transpose phi inverse into phi transpose y. So let us write down this in our, so let us write down this result in our slides. So theta ls is equal to inverse into phi transpose y. So we have this direct formula to get the value of the least square estimate of this parameter. So we have to just multiply this matrix phi, so phi transpose phi. So sorry. So phi transpose will be, so this matrix is 2 cross 3 and this is 3 cross 2. So phi transpose phi will become 2 cross 2. So basically 9 plus. Okay. So this is the value of the matrix phi transpose phi, and phi transpose y will be, so this matrix is again 2 cross 3 and this is 3 cross 1. So phi transpose y will become 2 cross 1. So the matrix phi transpose y is 18, 70 and 76. Now what is now we have to find out phi transpose phi inverse. So for that we will first find out what is the determinant of phi transpose phi. So what will be the determinant of phi transpose phi? So it will be 150 minus, so 50 into 3, which is 150, minus 12 into 12, which is 144. So 150 minus 144, so it will become 6. Sorry. So what will be the inverse? So it will be so the inverse of the matrix is 1 upon determinant A into adjoint of that matrix. So adjoint is the transpose of the matrix of cofactors. So let us write down the matrix of cofactors here, and then here it's a 2 by 2 matrix. So the cofactor for the first element will be 50. For the second element, the cofactor like so will be minus 12. The matrix like cofactor for this third element 12 will become again minus 12, and for the fourth element 2 cross 2 position, so it will be 3. So this is the adjoint of A. So the transpose of this matrix will be the same because the diagonal elements are equal. So will be, so 50 by 6 is just 25 by 3 minus 2 minus 2 and half. So this is phi transpose phi inverse. So we have to multiply this matrix phi transpose phi inverse with phi transpose y. So, so 25 by 3 into 18 minus 2 into 76. So which is 76 into 2 will be minus 150, it will be 76 into minus 2 will be minus 152, and 25 by 3 into 18 will be 25 into 6, which is 150, so it will be minus 2, and 76 divided by 2 will be uh, 38. So like minus 36, so minus 2 into 18, which is minus 36, plus 76 by 2, so 76 by 2 will be 38 minus 36, so which is again 2. So the least square parameter estimate is minus 2 comma 2. So basically A is equal to minus 2, and B is equal to 2. So this is our least square estimate of these parameters. So does that make sense? So shall we proceed with the next problem? Okay. Yeah, so before we proceed with the next problem, we can also try to solve this problem using MATLAB. So we can just quickly see how we can use MATLAB effectively for this kind of matrix multiplication kind of thing. So this problem involves like a lot of matrix multiplication. So we can just see how MATLAB can be used for this. So let us um, yeah. So let us first. So let me share my screen now. So I'm again sharing my screen. So are you able to see my like screen that I'm sharing? Okay. So let us go to our MATLAB window, and so we let us define our matrix phi in MATLAB. So which was uh, our phi matrix was, so our this is our phi matrix. So this is how we can define a matrix in MATLAB. And let us define our y matrix, which is so 3 comma. So to take the inverse of the like any matrix, we can do simply phi dash. So this will be our transpose. Sorry, so I'm sorry. So to take the transpose, we can just do phi dash, or we can also alternatively use the command transpose of phi. So this will again give the same answer. And to multiply these matrices, so phi transpose into phi, so we can use phi dash into phi, so which is 3 in 12, 12, 50. So this is phi transpose phi. And to take the inverse, so we can use the command matrix inverse inv. So we can use this command inv to compute the inverse. So inverse of phi transpose phi. So this is how we can compute the inverse. So our least square estimate of the parameter vector theta ls is phi transpose phi into phi transpose y. So we let us also try to calculate phi transpose, so phi dash which is phi transpose into y, sorry, into y, so which is 18 and 76. And now let us calculate now our least square parameter estimate, which is theta ls, which is phi transpose phi inverse, so which is inv inverse phi transpose into phi multiplied by, so let us put it into a bracket, so phi transpose into y, so this is our, so phi transpose phi inverse into phi transpose y. So our least square parameter estimate is minus 2 comma 2. So this exactly matches with our results that we just calculated. So this is how we can use MATLAB for simple matrix multiplication. So defining the matrices in the MATLAB environment and then using simple commands and using like inverse and transpose, etc. for MATLAB. So MATLAB can be also used like a calculator to for matrix multiplication. So it does it very well. So it does it very fast and very well. So and it's also user friendly. So this can also be used as a tool for calculating these things. So we saw that our math answer matches what we calculated just now with using hand calculations. So let us now proceed to our next problem. So in our next question, it is related to system identification. So ident toolbox, which is like basically the system identification toolbox. So it is used for analyzing what? Both. Okay, so it's used for analyzing both input as well as output signals. Yes, so ident toolbox will take these things, like the input signal and output signal values, and then use it use the various kind of models can be used. So we can try out various kinds of models, how they fit, how good is the fit between the the data, so that can be analyzed. So yes, so the correct answer is both. Yeah, so I think our next question, it seems to be a repeat of what we just discussed earlier. Black box in system identification is to choose a standard model and tune the parameters to the data. So the correct answer to this question is B. Let's move to the next question. Geometric constraints are useful to define what? C. Okay. So yes, you are right. So geometric constraints are used to define both the upper bounds and lower bounds on the design variables. So you are correct. So the answer is both A and B. So now let's come to our next question. So the graphical method is used when uh, yeah, so we have only like two design variables. So in case of two design variables, so the correct option is B. Yes, we can use it when we have two design variables. For one design variable, we don't need the graphical method, so it's just one dimensional. In case of three design variables, graphical methods may be difficult to visualize, but for two design variables, yes, we can do that easily. And for more than three design variables, it becomes so it's not possible to use the graphical method. So the golden section method applies to what? Single variables or multivariables or both A and B? Right, so the golden section method actually applies to single variable problems. So the correct answer to this question is single variable. Yeah. Now in our next question, we have been given that there is we are using, let us say, the golden section method. The interval of search is, let us say, 0, 3. So find out the interval of uncertainty after the fourth iteration using the golden section method. So for this, we have been given a formula in our slides, which is so for the nth iteration. So if the length of the interval in the nth iteration is in, let us say, and the initial length of the interval is, let us say, I0, so the formula for estimating the length of the interval after n iterations, so it is I0 in is equal to I0 into 0.618 to the power n minus 1. So after the fourth iteration, so I4 will be 3 into, so the initial interval length is 3 into 0.618 to the power 3. So what will be the length of the interval using this formula? So what will be the length of the interval using this calculation? Okay, 0.7081. So yeah, let us check that. So 0.618 to the power 3 into 3, which will be 0.7081. So yeah, so you're right. So the correct answer is B, 0.7081. Yeah, so in this questions, so we have been given that a firm manufactures products A, B, C. The profit for each of these products, like for A, B, C, are basically 3 rupees, 4, 2, and 4 respectively. The firm has two machines, M1 and M2, and so this is the processing time in minutes for each machine for each product. So machines M1 and M2 have 2000 and 2500 machine minutes respectively. So, the firm must manufacture 100 items of A and 200 items of B and 50 items of C. So we have to find out the objective function that maximizes the profit. So if x1, x2, and x3 are the uh, so let us say if x1, x2, and x3 represent the number of items or number of units of A, B, and C which are produced here. So then the objective function will be, so what will be our objective function? 3x1 plus 2x2 plus 4x3. Okay. So yeah, so to find out the profit, so we basically need to multiply the number of units of A multiplied by the profit per unit of A, so which is 3 into x1 plus 2x2 and 4 into. So this will be our objective function value for uh, this question. Now, based on this given data, we can also write down what are the constraints. So we have been given in this table this data of the processing time in minutes for each of these products like A, B, C. So we have been given like how much time it takes in minutes to produce this each of these items in machine M1 and M2, and the total time available on each of these machines M1 and M2 is given in minutes. And we have also been given that we must manufacture 100 units of A, 200 units of B, and 50 units of C. So the total processing time on machine machine M1 will be, so the time spent in making X1 units, sorry, so X1 units of A, so will be 4 into X1. So yeah, so let us write it down separately. So 4x1 plus 3x2 plus 5x3 is less than or equal to the time available on machine M1, so which is 2000, and the time available on machine M2 is 2500, so which we can write it down in a constraint as 2x1 plus 2x2 plus 4x3 less than or equal to 2500. So our objective is to maximize F, and we have been also given that we must manufacture 100 items of A, 200 items of B, and 50 items of C. So we can write it as x1 is greater than or equal to 100, x2 is greater than or equal to 200, x3 is greater than or equal to. So these will be our constraints of the optimization problem. And so we have also written the objective function value. So we can solve this problem. So since this is a three-dimensional problem, so because there are three design variables, so we cannot use graphical method directly here. So, but we can use other like methods like simplex method, etc. Whatever. So those are not out of the scope of this particular course for now. So this is how we can set up the optimization problem based on the description given in the problem. So this is how we can formulate it, and I also have so this was about for these problems, and then we have like I still have some more problems for you. So you can try those problems on your own, and we can if you have any doubts or any difficulties, we can discuss that. So you can try them, and that if you have any questions, so you can let me know. So so that's all that I have from my side. So this was the last session for uh, this particular course, and so I think after that you will be having your exams. So I wish you all the best for this the exams, and I hope you found these problem solving sessions useful. So yeah, so that's all that I had from my side. So all the best, and yeah, thank you for joining this session. Sure. So I think we can end this session for today. So yeah, good night.